Hello everyone, my name is Julien Ferry. I'm a postdoctoral researcher at Polytechnique Montréal, and I'm going to present a work entitled Trained Random Forests Completely Reveal Your Dataset and appearing at ICML 2024. This is joint work with Professor Ricardo Fukasawa, Timothée Pascal, and Professor Thibaut Vidal. What we show in this work, in a nutshell, is that the structure of a trained random forest can be used to retrieve all or almost all of its training data. So we really raise awareness against publishing trained models and in particular trained random forests. For this presentation, I will first provide some background notions. Then I will show with an illustrative example how the structure of a decision tree or of an ensemble of decision trees can be used to reconstruct its training data. Then I will present with more details the framework we proposed to reconstruct the training set of a random forest, which is coined DRAFT for dataset reconstruction attacks from tree ensembles. Then I will present an experimental evaluation of it, and finally I will conclude. So we consider labeled datasets that are composed by a number of examples, n, each example being characterized by a vector of m binary attributes and by a class. We have here an example dataset with 4 binary attributes, f1 to f4, 1 binary class, and for example, 1 per row. In the case where several binary attributes come from the one-hot encoding of the same original feature, we know that they have to sum up to 1, and this is an information we may have. So we will use vect to denote the list of the different groups of binary attributes one-hot encoding the same original feature. This is an information a framework can use, but it is absolutely not required. For this presentation, we focus, as you can say, on binary attributes, but again, this is not a limitation of a framework, and we can handle categorical attributes, ordinal attributes, as well as continuous attributes within our proposed framework. And the code, which is online, also handles all these different cases. With such a dataset, we can train different machine learning models, and these models can be decision trees. Here you have an example decision trees using the popular scikit-learn library on the dataset I showed previously. As you can tell, a decision tree is made of a set of internal nodes. Here we have 2 internal nodes, and a set of leaves. Here we have 3 leaves. For each node and each leaf, we have the number of training examples from each class that went through it. This is an information provided by default by the scikit-learn library, and it's also usually provided because it allows the computation of confidence scores for each leaf. Here the leaves are pure, but it may not be the case. And it's in general not the case. What we say here is that we have 2 examples from class 0 and 2 examples from class 1 in the overall dataset, which indeed was the case. And out of all of these examples, 1 example from class 1 went here, and so on. For every leaf, we will use this notation to denote the set of indices of the binary attributes that must be 1 for the example to fall into this leaf. And similarly, this notation will be the set of indices of the attributes that must be false for the example to fall into this leaf. So for instance, for this leaf, for an example to arrive to this leaf, attribute f3 has to be false, while attribute f2 has to be true. This was a single decision tree, but to obtain more complex models, we may want to learn forests that are sets of decision trees. Because we do not want to learn several times the exact same trees, we will use several randomization mechanisms during training, and what is usually done is that only a subset of the attributes are considered when choosing which attribute and which value to split on at each node. Another popular mechanism is bugging, which stands for bootstrap aggregating. It consists in generating different training sets, 1 for each tree, using sampling with replacement, usually from n examples to n examples. So you have the original training set of the forest with n examples. You perform sampling with replacement to generate a new training set for the first tree, and you do this iteratively for the different trees. And so at the end, for a given tree, some examples will be used several times, and some others will not be used at all. And finally, the last building block is dataset reconstruction attacks, which is what we want to do in this work. So reconstruction attacks are a type of inference attacks which were first proposed against database access mechanisms, and their objective is to retrieve entirely or partly the dataset used as input of some algorithm by only observing the outputs of the algorithm. So in the machine learning field, the output is usually a trained model and its parameters. The computation itself is the machine learning algorithm, and the input dataset is the training datasets. More precisely, we consider the setup where an adversary has white box access to a trained random forest, and the objective of the adversary is to reconstruct as accurately as possible the training sets that was used to train the forest. Okay, now I will show with an illustrative example how we can leverage the structure of a decision tree to reconstruct its training set. We will first do it for a single decision tree, and then we'll see how we can do it for an ensemble of decision trees and which are the main challenge we'll have to face. Okay, so here we have the exact same data set that I showed previously, the decision trees that I showed previously, which was learned on this data set. And what we can see is that the structure of the tree allows retrieving part of the attributes of the examples within this data set. For instance, if we look at the root node here, we know that 2 examples from the training sets belong to class 0 and 2 belong to class 1. So we can indeed reconstruct the entire class column here. Out of this, for example, one example from class 1 went on the right here, which means that attribute F3 was 1. And this corresponds to this attribute. If we follow the different branches and perform the domains reductions for the corresponding attributes, following the splits on the nodes, we can actually reconstruct from this simple decision trees with only 2 internal nodes all the values that are bold here. This simple reconstruction process was introduced in the literature, again for a single decision tree, and was later generalized for other types of interpretable models, in particular rule-based models. What if we now have not a single decision tree, but several decision trees trained on the same dataset? So here we have the same dataset showed previously, the same decision tree, but we also have an additional decision tree here, which was trained on the same dataset with different random parameters for the choice of the attributes here. So again, we can, by only observing the first tree, retrieve all the values that are bold, but by observing the second one, we can also retrieve all the values that are underlined. And by matching the information coming from the 2, we can actually retrieve all the values that are either bold or underlined. And this means that here we can retrieve all the values within this dataset except this tree. So almost all the datasets. However, this was a very simplified version of the problem because we only had 2 decision trees. So how to match the information provided by different trees, because this is incomplete information, is challenging when we have more than 2 trees. And the second question is, what if bugging is used? On the toy example that I just showed, the 2 trees were trained on the exact training set. However, when bootstrap sampling is used, each tree within the forest is trained on a different sampling of the same training set. So the counts provided within each node of each tree actually count some examples several times and some examples not at all. So how to deal with this is a real challenge. To face these different challenges and perform dataset reconstruction against tree ensembles, and in particular random forests, we propose drafts, which I'm going to depict in this section. So I will first explain the high-level principle of our approach, then I will provide the formulation we propose for the simplified case where bootstrap sampling is not used, and finally I will depict the whole formulation, including the case where bootstrap sampling is used to train the forest. So recall the setup. We consider an adversary as white box access to a trained random forest, and the objective of this adversary is to reconstruct as accurately as possible the forest's training set. In our paper, we show that this reconstruction problem is NP-complete, so it is theoretically difficult. However, we propose to solve it using mathematical programming approaches, and in particular mixed integer linear programming and constraint programming models. For this presentation, we will focus on the constraint programming models, which is why they are bold here. The general idea is that we will use these declarative programming approaches to encode the structure of the trees within the forest. Each tree will define a set of constraints, and we will leverage general purpose solvers to find feasible reconstructions, so feasible values of the different attributes of each example, given all the provided constraints. When bootstrap sampling is used, we will use additional variables modeling this bootstrap sampling process, and we will maximize the likelihood of this variable's assignment, given that we know the known theoretical probability distribution of bootstrap sampling. So this is the constraint programming model we can use when bootstrap sampling is not used. So it's a way to solve a simplified version of the problem. For this version, we only need two types of variables. The green variables will model the reconstructed example's attributes. So xki will simply be the value of feature I, for example, k in the reconstruction. And the blue variables will be useful to assign the different examples to the tree's leaves. So ytvk will be 1 if example k was classified by leaf v within tree t. Note that here, because bootstrap sampling is not used, each example is used exactly once within each tree. And so we can pre-assign the different classes. So zkc here will be a constant, which is a one-hot encoding of example case classes. This is important because here we can do it when bootstrap sampling is used. We will no longer be able to do this, and zkc will become a variable. Now we can set constraints modeling the structure of the forest, the knowledge we have on these variables. We first want to ensure consistency with respect to the one-hot encoding information. Again, this is not related to the forest, and this is absolutely not mandatory. It may help facilitate reconstruction, but it's absolutely not mandatory. And then these are the constraints modeling the structure of the forest. So we want each example to be assigned to exactly one leaf within each tree. We want the number of assigned example for each node of each tree, for each leaf of each tree, to match the provided number within the tree structure. And if an example is assigned to a given leaf, it has to satisfy all the split conditions within the branch leading to this leaf. The solution of this model is an assignment of all the attributes of all examples. So it's simply a feasibility problem. If we now consider the general case where bootstrap sampling is used, we have to extend this model a little bit. So we still have green variables modeling the reconstructed examples, attributes, and class labels. The xka were already in the previous model, but now we also have zkc, which are the classes of the different training examples, which cannot be prefixed now. We still have blue variables assigning the examples to the tree's leaves, but now they are no longer binary because an example can appear 0 times, 1 times, 2 times, or more, because the training sets of the different trees are generated using sampling with replacement. And we have additional red variables which one-hot encode the bootstrap sampling process. So qtkb will be 1 if training example k is used exactly b times to train tree t. B here is the number of times an example is used to train each tree. So it's theoretically between 1 and n, but the probability that it's greater than 5, 6, or 7 is really small. So we can, in practice, put a value of the upper bound here, which is smaller than that. With these new variables, we can again define a set of constraints which model the knowledge we have. Again, we may have information regarding one-hot encoding, and in such a case, we will ensure consistency, but this is not mandatory. And then we have all this information corresponding to the forest structure. We want each example to be assigned to exactly one class. An example can only appear in its class counts, so if it doesn't belong to class C, it cannot appear anywhere in the counts corresponding to class C. We want the number of assigned examples to match the provided counts here, but now an example can account for more than 1, since these variables are integers and not only binary values here. And if an example is assigned to a given leaf, it has to respect all the conditions corresponding to the splits along the branch leading to this leaf. The last constraint here is only helpful to retrieve, to one-hot encode the value here of the y variables. So this is a one-hot encoding of the number of appearances. They will be useful to formulate our objective function, which I'll just show. So this problem as is simply a feasibility problem, and because we allow the solver to choose for each example a number of occurrences, we add a lot of freedom, and actually this model has many possible solutions. So we will try to orient the search towards the most likely ones, and to do this we will leverage the fact that we know the theoretical probability distribution of sampling replacement. So this is the probability that an example appears b times in the training set of a given tree. So these are the b times where the example is selected out of n candidates. These are the n minus b times where it was not selected, another one was selected. And these are the different sequences. So this is a constant which can be pre-computed basically. Then the overall probability of a given assignment of the bugging variables can be computed using this big product, which is nonlinear, and so we will instead maximize the log probability, which is equivalent, but now this is a linear expression which is here. And again, recall that this is a constant. So this expression is linear, and this will be our objective function. We will maximize the likelihood of the assignment of the bugging variables. Okay, now I have presented our proposed framework, and we will see in practice how it works with an experimental study. First, I will describe our experimental setup, then I will present some results, and I will also detail additional takeaways that we can have from these experiments. So we first learn different random forests using the popular scikit-learn library. We learn them using bootstrap sampling or not. We consider forests with varying number of trees between 1 and 100, which is the default value of the scikit-learn library. We consider maximum depth constraints for each tree. So we consider trees of depth 2 up to known, which stands for no maximum depth constraints. And we learn all these random forests on 3 different data sets, which are shown here. Importantly, for the experiments presented within this slides, we randomly subsample a training set of size 100, but in practice we show that the method can scale up to values larger than that. Once the random forests are learned, we will run a reconstruction attack to reconstruct training sets from them. So we will use the OOTools CP-set solver to solve our CP formulations. We will limit each run to 5 hours of CPU time. This is mainly for the bugging formulation because it's an optimization problem. But without bugging, this is simply a feasibility problem, which is in practice often solved in seconds or minutes. When using bootstrap sampling, the solver is often able to find feasible solutions within minutes as well, but we leave it more times to improve the solution. We will compare our results to a random reconstruction baseline, which is aware of one-hot encoding and which actually models all the knowledge we can have, except that coming from the random forest itself. So this random baseline knows the one-hot encoding information. It produces random reconstructions that are consistent with the one-hot encoding. It also knows the number of examples and the number of attributes. And so what matters in our results is the difference with this baseline, because it really comes from the knowledge coming from the structure of the forest. Once we have performed the reconstructions, either with our method or with the random baseline, we have to compute an error, and to do so we first align the original and reconstructed datasets using a minimum cost matching. So this answers the question which reconstructed example corresponds to which training set example. And once this alignment is done, we compute the average Manhattan distance between each original example and its matched reconstructed counterpart. And by averaging this value over the entire dataset, we have an average reconstruction error. The results are average for each experiment over 5 random sets. Okay, these are the results we obtained for the Compass dataset. The figure on the left corresponds to the simplified case where bootstrap sampling is not used, so it is the first constraint programming model that I showed. and the results on the right correspond to the general model where bootstrap sampling is used. On the y-axis, we have the reconstruction error, so the proportion of attributes that differ in the reconstruction compared to the actual training set. So a value of 0 here means that we have exactly reconstructed the training set perfectly. And the y-axis here is the number of trees within the forest. The different colors correspond to different maximum depth constraints. What we observe if we look at this curve here is that when bootstrap sampling is not used, even with only 5 or 10 trees, we are able to reconstruct the entire training set of the forest, provided that the different trees are deep enough. When the trees are really shallow, for example, for trees of depth 2, we are able to leverage their information, but we cannot reach perfect reconstruction. So the deeper the trees, the more information we have, which makes sense. And the more trees we have, the more information we have. But importantly, even with a limited number of trees, and even if they're not that deep, we can here retrieve all the training sets. When bootstrap sampling is used, these two trends are the same. Deeper trees provide more information, more trees provide more information, but we do not reach here a perfect reconstruction. We have a kind of residual error here. These trends are the same for all data sets. So these are the results for the adult income dataset. Again, without bootstrap sampling, we are able to reconstruct the entire training set exactly. With bootstrap sampling, we have a residual error, even if it's kind of low. Deeper trees provide more information, so lower reconstruction errors, and more trees provide more information. And these are the results for the default of credit card client datasets, on which the trends are even more obvious because this is the largest dataset in terms of numbers of attributes. What we didn't see in these curves was the runtime of the attack. So for this slide, we fixed the number of trees in the forest to 100, which is the default value of scikit-learn. And we vary the maximum depth constraint for the 3 data sets between 2 and no maximum depth constraint. What we observe first is that where bootstrap sampling is not used, for the simplified version of the problem, the solver is able to find the reconstruction within seconds or minutes. It only fails for a few number of cases here. When the trees are really shallow, for example, when they have a maximum depth of 2, the solve time is really small because in practice there are many possible reconstructions. And when the trees are really deep, the reconstruction times are also small because the problem is over-constrained. So there are actually not a lot of feasible solutions and they often correspond to the true training set. The most difficult cases arise where the problem is not under constraint, no over-constraints, which appears here when the trees are not too deep nor too shallow. And we see here that these running times are significantly larger, and we even have some fails here. When bootstrap sampling is used, we do not report runtimes since this is an optimization problem and we allow a given time window for the solver to improve in terms of objective function the solution. So we only report the number of fails here, and what seems to matter is only the size of the problem. So deeper trees provide larger models, and for larger models the solver may struggle a little bit, so we have some fails here for the largest instances. Now we fix the maximum depth constraint to the default values, which is no maximum depth constraint, and we vary the number of trees in the forest here, again for the 3 data set. And what we observe without bootstrap sampling, but also with bootstrap sampling, is that only the size of the problem matters here, and more trees lead to larger models and higher running times in the no-bugging case, and more failures in the bugging case. We also have additional interesting takeaways from these experiments that are not shown in this presentation. In particular, we tried to understand why, when bootstrap sampling was used, we had this effect where we didn't reach perfect reconstruction. It turns out that if the adversary is able to correctly guess the number of occurrences of each example within each tree's training set, so is able to correctly assign the value of the bugging variables, then reconstruction accuracy is as good as in the non-bugging case, and actually even better because the trees are more diverse. Which means that this difficulty inherently comes from the randomness introduced by bugging. And this matches results from the literature stating that bugging provides a form of differential privacy protection. Because it introduces randomness, it actually produces noise in the random forest, and this noise protects the training data. We also performed partial reconstruction experiments, so we assumed partial knowledge of the training set, and we tried to reconstruct the remaining attributes or examples. We observed that if some attributes are known, which may correspond to the case where some attributes correspond to public information, it helps reconstructing the others, but when some examples are known, it doesn't really help reconstructing the others, and again it may be due to the fact that bugging provides a form of differential privacy protection. We also performed experiments with datasets larger than 100 examples. In practice, we went up to 1,500 examples, and we observed that the solution time scales approximately quadratically with the number of examples, which is considerably better than the theoretical worst case, which is exponential since the problem is NP difficult. So the method is actually quite scalable despite its theoretical difficulty. Again, we also have mixed integer linear programming formulations, but we didn't show them in this presentation since the results in practice, the constraint programming formulations scale better. Okay, so to conclude, we propose in this work a way to use mathematical programming techniques to build new paradigms of data reconstruction attacks against machine learning models. We show that even if the problem of dataset reconstruction from trained random forest is theoretically difficult, it can be solved efficiently in practice using the formulations we provide. And our main insight is that trained random forests actually give away most of the training data or all of the training data. So this result really raises awareness on the dangers of releasing trained models, because often when you release your trained random forest, it's equivalent to releasing your entire training data, which you may not want to do. Future works include the handling of other types of attributes, but as I mentioned, this is already done in the implementation, but also using a similar strategy on other machine learning models, other types of tree ensembles, but also other types of models like neural networks. Improving the current models by including additional constraints, for instance, modeling the behavior of the training algorithms. If we know, for instance, that a given information gain criteria was used to select the splits within each node, we can leverage this to include additional constraints within the constraint programming model, and this will help get either better results or faster results. And finally, developing and benchmarking protection measures, for instance, by learning differentially private random forests, is an important research avenue to avoid such attacks in the future. As an interesting epilogue, as I mentioned in the experimental evaluation, bugging provides a form of protection because this random sampling process adds noise in the cans provided within each tree's nodes. So the difficulty when bugging is used really comes from guesses the number of occurrences of each example within each tree's training set. And just after we sent the paper to ICML, scikit-learn made a new release where they provide this information through a new attribute. So this again illustrates the fact that sometimes when you provide additional information regarding a model, even if this information is not the training data itself, it may be used to infer the training data. Thank you for this presentation. Here is my contact. If you want to reach out, don't hesitate. Our source code is available on the internet. Don't hesitate to play with it. Our article is also available online. And again, this is appearing at ICML 2024 for both a poster and an oral presentation. Thank you.